Welcome to Calculus. Today we will investigate differentiating rational base logarithmic functions. We've got a simple example to start here, but before we can take its derivative, we need to write the rule. How do I take the derivative of a logarithm with a rational base? Really, what we're looking at mostly is natural number bases. So where we start is with the relationship between a logarithm and an exponential. So before we begin, let's write the rule to take the derivative of this function, y equals log base a of x. So what we've got to do first is remember that the essential relationship between the logarithm and the exponential would be that if I've got y equals log base a of x, that's equivalent to x equals base a to the power of y. So to make our rule, I want to use implicit differentiation on that exponential equivalent. So let's write the derivative with respect to x of the left side x equals derivative with respect to x of a to the power of y. So on the left-hand side, the derivative of x is going to be just 1. And then on the right side, the derivative of, with respect to x of a to the power of y, if I apply my exponential differentiation rule, that's going to be a to the power of y times the natural logarithm of a, and then I've got the differential dy dx. And that's from the chain rule. So at that point, I want to solve for dy dx. So I'm going to divide both sides by a to the power of y times natural logarithm of a. So that'll cancel there on the right side. And it will show up in the denominator on the left. And I'm going to switch the equation around now so that it's solved for dy dx. And that really is our rule, but I need to do a substitution. So I'm looking up at my original work, and I'm seeing that a to the power of y essentially was the same as simply x. So I can make that substitution kind of immediately. So this becomes 1 over x times the natural logarithm of a. And that is the rule that we can use here when we're going to take the derivative of a function like y equals log base 3 of x cubed. So let's do so. We got our rule. So we're interested in the derivative of y. So we'll start off just by noting that this is a composed function within the logarithm function. So that means as we apply the logarithm base a rule, I also need to apply the chain rule. So I'm going to write 1 over that composed function unchanged, x cubed. So what that would be equivalent to is my x there, that's where the composed function would rest, times the natural logarithm of the base, which here is 3. And then applying the chain rule, I need to take the derivative of the composed function, x cubed. So that's going to give us 3. The old power is a coefficient times x to the power of 3 less 1. So we just have to simplify our answer here. So the 3x squared would go to the numerator times 1 over x cubed times the natural logarithm of 3. And then I have some final cancellations here. X squared would cancel with all but one of the x's below. And what we get is y prime for a final answer is 3 over x times the natural logarithm of 3. And that completes that first example. So we built the rule there And then we applied the rule to take the derivative of that simple logarithm function. Let's take a look at a second example that involves a logarithm of a logarithm. So here I've got y equals logarithm base 5 of logarithm base 5 of 5x to the power of 5. So if you've got this arrangement where really you've got, in effect, two composed functions, you could think that this really is f of g of h of x. It looks a little bit daunting at first, but really all it requires is application of the chain rule twice. So we'll start, we're going to apply our rule again, so let's get that in view. So if we've got y equals log base a of x, the derivative of y is going to be 1 over x times the natural logarithm of a. That's the rule we had just written at the outset. So I just need to apply it using the chain rule twice here, again, because I've got a double composed function. Let's just identify which is which piece. So the f of x is going to be this first logarithm. The g of x is going to be the second logarithm. And then the h is going to be 5x to the power of 5. So that kind of gives you an idea about how we're arranging the derivative here. So we'll start with that outer function. We're going to take derivative of log base 5 of, really we'll consider that as one thing, log base 5 of 5x to the power of 5. So as we begin, the derivative of y is going to be equivalent to 1 over, so I'm just using my rule here. So this whole piece is going to go in for the first application of chain rule to that x. So it's going to be over log base 5 of 5x cubed, and then times the natural log of that base, which is 5. Now I need to keep going because now I need to apply chain rule. I need to take now the derivative of the composed function. So you just keep going with the chain rule. So the derivative of the composed function is going to be also applying our logarithm differentiation rule. So that one's going to be 1 over, so now I'm taking derivative of what's highlighted in green. So that's the composed function 5x to the 5th times the natural log of the base on that logarithm, which is also 5. But then I have that third composed function. So let's highlight that one in blue, 5x to the power of 5, which again, I need to take derivative of using the second application of the chain rule. And that one's using just our simple power rule. So I'm going to leave the constant multiplier of 5, bring the old power of 5 down, x to the power of 5 minus 1. And at that point, we've done the full double application of the chain rule. And so what remains for us to do is just to combine like terms, simplify, and reduce the answer. So now what I see for my numerators, I've got 1 times 1 times 5 times 5 times x to the power of 5 minus 1, or 4. So all that multiplies to 25 x to the power of 4. For my denominators, I've got log base 5 of 5x to the 5th times natural log of 5 times 5x to the power of 5 times natural log of 5. So what I'll do is I'll take this factor highlighted in blue, 5x to the power of 4. I'm going to bring that out front, times the logarithm base 5. This is what is highlighted in green, 5x to the power of 4. And then I have two factors, natural log of 5. So that's natural log of 5 squared. So we've got it all in one fraction. We just need to cancel anything that is cancelable. And let me make sure I get my power correct on this denominator. should be 5x to the power of 5. So there's a cancellation there. The 25 divided by 5 will leave 5 in the numerator. X to the 4th divided by x to the 5th will leave an x in the denominator. So our final answer here is going to be 5 over x times the logarithm base 5 of 5x to the power of 4 times the natural logarithm of 5 squared. And that completes the derivative of that double logarithm. So our first example, we just had to apply chain rule 1. Second example, we had to apply chain rule twice. For our final example, what we want to look at is a function that requires us to apply logarithm equivalency rules, rewriting the function before we differentiate. So let's zoom there. Our last example is this function, f of x equals log base 3 of 5x to the power of 5 over 3x to the power of 4 plus 1 quantity squared. So what I want to do is I want to expand this logarithm first and then take the derivative using my rules, and then simplifying the answer from there. But before I can take derivative, I need to unpack this kind of enormous argument. So recall from our logarithm rules that I can bring this power out as a coefficient first. So I'm just going to start rewriting this logarithm. It's going to be 2 times the logarithm. And then the second change I need to make is applying the quotient rule for expansion of a logarithm. Remember, that's equivalent to log base 3 of 5x to the 5th, the numerator, minus, so the quotient there converts to a subtraction or a difference of log base 3 of the denominator 3x to the power of 4 plus 1. So with that expansion, what I'll do then is I want to distribute back this 2 just to simplify. That was a little too far. To simplify the differentiation process. So what we're going to work on is this version of f of x. It's expanded to be 2 log base 3 of 5x to the power of 5 minus 2 times log base 3 of 3x to the power of 4 plus 1. So once I've got it into that expanded form, now I can apply my differentiation rules. So we'll call f of x here, let's just call that y. So now I'm going to find the derivative of y, so y prime. So I'm going to work on this first logarithm to begin. So we got the constant multiplier 2 that just sets out front. And then I want to apply my derivative of a logarithm that we wrote at the outset. So that's going to be 1 over, now I've got a composed function there, 5x to the power of 5. So that's going to go first where the domain value x would be, times the natural log of the base, which in this case is 3. And because I had a composed function, something other than x there in the argument of the logarithm, I need to take its derivative to satisfy chain rule. So now I'm going to multiply times 5, the old coefficient, and then times the old power 5, now a coefficient as well, x to the power of 5 less 1. And that takes the derivative of that first expression. Now we need to take the derivative of the second. So I do need to apply the difference rule for differentiation. I'm just going to write minus. Remember, that just says we take the derivative of each term in the difference separately. So that's going to be 2 again, the old multiplier just setting out front. And then again, applying my logarithm differentiation rule that we wrote. It's 1 over Just like we saw before, I've got a composed function in this second term as well. That's going to rest where the domain value x is in the rule. So I can see I'll need to apply the chain rule for this term as well. And this is also times the natural logarithm of the base 3. Just to say which term we're working on, let's highlight it in green. So now to catch the rest, I need to take the derivative of the composed function. So that would be 3, the old coefficient, times the old power 4 down as a coefficient, x to the power of 4 less 1, plus the derivative of 1 is 0. So that's the derivative. Once I've taken it, I need to simplify, and if I can, write that as one fraction. So let's simplify the fractions, and then we just need to combine them by getting the same denominators. So what I see first is that I've got numerators 2 times 1 times 25 x to the power of 4 for this first term. So that's going to be 50 x to the power of 4 over 5x to the power of 5 times the natural log of 3. Let's go ahead and cancel any terms that would reduce above and below. So 50 divided by 5, it's going to leave 10 in my numerator. And then x to the power of 4 divided by x to the power of 5 will leave x in the denominator. So for my next step, if I just want to kind of finalize this first term, it's going to be 10 over x times the natural log of 3. That reduces down a lot. Our second term, let's make the initial simplification into a simple numerator-denominator setup. So it's going to be 2 times 1 times, I'll let the 0 fade away, 3 times 4 is 12, x to the power of 4 minus 1 is 3. So that's going to reduce down to 24 x to the power of 3 all over 3x to the power of 4 plus 1 times the natural log of 3. So there's no cancellations there because I've got a binomial, 3x to the power of 4 plus 1, and that prevents any reduction above and below for that second fraction. So I'll just write it down below. And what we need to decide is how can I combine that now as one single fraction. And remember, when you're combining fractions by subtraction, the big consideration is the denominators need to be identical. So my least common denominator here is going to be the natural log of 3 times x times 3x to the power of 4 plus 1. So the piece I'm missing here on the first quotient is going to be the 3x to the power of 4 plus 1. So I'm going to multiply that above and below. What I'm missing from the second quotient is the x. So with those scalings, let's go ahead and we'll write to the right side here so we can keep it in view. That's going to give us, if I distribute the 10 through the 3x to the power of 4 plus 1, that'll be 10. Well, I said I was going to distribute. That'll be 30x to the power of 4 plus 10 minus, and then from the second term's numerator, 24x cubed times 4 would be 24x to the power of 4. And now we're in one fraction, so I'm going to create that common denominator, x times 3x to the power of 4 plus 1 times the natural logarithm of 3. And then the last simplification I can make is combining like terms in the numerator. So 30x to the power of 4 minus 24x to the power of 4 is going to give us 6x to the power of 4 plus 10 all over that same common denominator, x times 3x to the 4th plus 1 times natural log of 3. And that is going to be our final answer. Thank you for joining for this investigation of differentiating rational base logarithms. I'll let you differentiate your own natural base logarithms. See you soon.